I'll be presenting a paper called Déjà, which is on looping transformers for multi-view 3D reconstruction. Before I start, although this talk is about 3D reconstruction, the core idea is about reusing transformer blocks through in a recurrent manner, which can also be related to VLMs or LLMs. So even if you are your main research area is not 3D, I hope there will be still something interesting for you in my presentation. This is the demo of Déjà, and let me briefly explain about the task. Given multiple uncalibrated images, the model predicts the 3D geometry of the scene, which consists of camera poses, depth maps, and ray maps. You can see that the scene is reconstructed with 3D points clouds from depth map and camera poses. And here is the main result of Déjà. The size of the circles are indicating the number of parameters. And you can see that it achieves strong depth and camera pose accuracy with much smaller parameters compared to other computing methods. Before presenting about how they achieve this result, let me introduce about 3D reconstruction task first. 3D reconstruction has been a key research problem in 3D computer vision for a long time. This task aims to recover 3D point clouds in camera poses of the scene from several input uncalibrated images. Classical methods like column map reconstruct geometry by matching input images and performing person optimization to get accurate camera poses and 3D point clouds. And this is more recent 3D reconstruction method called VGT, which won the Best Paper Award in CPR 2025. Instead of performing person optimization like column map, which can be really slow, VGT predicts 3D geometry directly from input images in a feed-forward manner using learned prior. And this is an overview of VGT, which consists of a large transformer, and it is trained on large-scale multi-view datasets to perform feed-forward 3D reconstruction using learned prior. Recently, the major research field has been moving from classical person optimization method to feed-forward method. Person optimization methods such as column map are reliable when there is enough texture and large number of input images. But they are slow due to the person optimization, and they often struggle with challenging scenes like if there are sparse images or textureless and repetitive scenes. In contrast, feed-forward methods such as VGT are much faster and can work in more challenging settings like sparse input images. However, their geometric reliability depends more on the training distribution, and it's really difficult to check whether the predicted geometry is accurate or not. Despite these limitations, feed-forward approaches have recently become an active research direction due to its practicality. And I'm going to introduce you about feed-forward method today. In recent years, feed-forward methods such as Duster, Monster, VGT, PyCube, and so on, they all improve feed-forward 3D reconstruction. But as shown in this plot, the number of parameters also keeping increasing. In this context, we can ask a question like, is this a really desirable research trend? Nowadays, as AI models becomes larger, they consume more computational resources and electricity. And it raises concerns about their environmental impact. Déjà started from this observation and suggested a resource-efficient model model architecture using very small number of parameters compared to the previous method, while maintaining the performance. This is the core idea of the paper. In BridgeT, large number of transformer blocks have their own parameters. In contrast, Déjà, they use a single loop transformer block and apply it k times recurrently. So the model does not need separate independent parameters for every step, while it still performs multiple steps of computation. The same block is reused iteratively, and this is why the model can be much smaller. This idea is motivated by a prior work on block recurrence dynamics in vision transformers, which is published in iClear 2026. This prior work shows that token features in nearby reality layers are often shows high similarity, as shown in this figure. The yellow one denotes the high similarity, and blue one denotes low similarity. This suggests that some layers may be doing similar types of computation, and it would be redundant to use independent parameters for every layers. Based on this finding, they try to cut the transformer depths into a small number of blocks. The idea is to group similar layers of the transformer. For example, instead of treating all 11 layers as independent, they divide them into 2 or 3 recurrent blocks. This is to check the hypothesis. If layers inside the block are similar, then maybe one shared block can approximate them. I'm going to explain this part in detail using this 2 blocks cut example. They first cut transformer into 2 blocks, and they train this cutted transformer with knowledge distillation techniques. As shown here, they train a student model using only a few recurrent blocks. The teacher is the original Dino2 model, where every layer has independent parameters. The student reuses only 2 blocks, and each block is applied multiple times. They also add time variant information, so the same block can behave differently depending on the iteration times. This implies that iteration does not mean doing exactly the same thing every time. It means the model uses the same parameters, but performs step-dependent operation. The result is quite interesting that even with only 2 or 3 recurrent blocks, the student model achieves performance close to the original reality, which is Dino2 in here. And with 3 blocks, it recovers most of the original performance on ImageNet classification. This supports the idea that full independent parameterization may not always be necessary. The takeaway from the prior work is that variety depths can contain repeated computation, and this supports the idea that VIT can be implemented with a small number of recurrent blocks, not many independent blocks. And here is another prior work motivating the recurrent block, which is about 3D reconstruction transformer. This work shows that the star, which is a 3D reconstruction transformer, does not predict perfect geometry at once. Instead, it first predicts coarse geometry and then progressively refines it across decoder blocks. Together, these prior works suggest that benefit of large 3D reconstruction transformer models arises from implicit iterative refinement, and layer-specific parameters can be redundant. Motivated by these findings, Déjà asks a question that what if we implement 3D reconstruction transformer with a single recurrent block? And this is the transition from implicit iteration inside the deep model to explicit recurrence in the architecture. And this is the main pipeline of Déjà again, and they first extract image features using DynoV2 and feed them these features into a loop transformer block. This block is applied k times with shared parameters, and after the recursion, they add the final state to decoder branches. The input is a set of multiple images, and the model outputs camera poses, ray map, and depth maps. And actually, this problem setup is just follows the prior work depth anything 3. Let me introduce you about the loop transformer block in detail. Inside the looped block, they use two types of attention. The first is frame attention, which operates within each image, like you can see in this figure. And the second is global attention, which operates across all frames. This makes the model compare information between views and reasonable multi-view geometry. And actually, this design follows the prior work BGT, and this is a kind of convention in 3D reconstruction transformers nowadays. And they formulate the recurrence over a time interval from 0 to 1. At each step, the state is updated using the same loop block conditioned on the ground time interval like tk and tk plus 1. This time conditioning is useful since the same block must behave differently at different refinement stages. And this is attention layer in ordinary transformer blocks. However, when we use this attention layer for recurrent transformer, it can be unstable since the same residual blocks are repeatedly many times, and the features can be exploded. To avoid this, they add scale vectors. There are two types of scale vectors. The first one is time invariant scale vectors. These control the base magnitude of each residual update, and they help keep the residual update small and stable. The second is time variant scale vectors. These are generated from the time interval tk and tk plus 1. So they modulate the shared block differently at each refinement step. Actually, these time variant scale vectors are, you can think it's like learned embeddings, which is generated from MLP in here. And in short, the scale vectors let the model reuse one block while still making each iteration behave differently and safely. And this is another detail about the recursion step K. During training, they sample K from 8 to 16 using a beta distribution. This means that the model learns to operate with different numbers of recurrence steps. And this enables users to choose the number of recursion steps in the inference time. So when they use smaller k, it would be faster but inaccurate. And when they use large k like 16, it would be accurate but kind of slow. And this is the training loss. And they also use training loss following depth anything 3, which is a prior work. And this provides depth gradient, rays, 3D points, and camera poses. So the model can learn both depth and camera geometry. And I'll skip the details since they just follow conventional rules from the prior work. For training data, they use 29 multi-view or video datasets, which is really large scale. And these are quantitative results. On point map and current post metrics, Déjà performs strongly across benchmarks. And actually, this table is more important than the previous one. Déjà use only 117 million parameters. In contrast, models like Vgt Omega, which is a recent state-of-the-art 3D reconstruction transformer, and it uses much more parameters than Déjà while Déjà achieves the better average performance in across 5 benchmarks. And it also shows smaller compute and memory overhead, as you can see in these columns. And this is the qualitative result. Compared with the larger baselines, the reconstructed object and the scene with Déjà look more clean and complete. And this slide shows how the output changes as the recursion step k increases. More iterations lead to more complete and more stable reconstruction. This visualization supports the idea of iterative refinement. The recurrence block does not solve the scene in one step, and it improves the reconstruction step by step. And the evaluation study shows about the effect of their block design. The decoupled baseline uses independent parameters and performs worse in the first row. And when they use shared recurrence, performance improves, even though the model has far fewer parameters in the second row. Then adding residual gates and state gates, which denotes time-conditioned embeddings, as I mentioned in previous slides, further improves performance. And this is the experiment about the number of iteration steps. Since the model is trained with iteration step k between 8 and 16, when they test much larger k, performance gets worse instead of improving. So variable k gives flexibility, but only inside the training distribution. And I think this is a really natural result because they use learned embedding for time step condition. And this is another experiment showing iterative refinement. The figure shows that the visualization of global attention, and it shows the course to find correspondence search. Early iterations are broad, while later iterations focus on more precise matching regions. And this is another experiment to better understand the recurrence. They analyzed the hidden states across iterations in here ZK, which is token features in between the layers. First, they compute the cosine similarity between the state at iteration k and the final state, which is k equal to 16. The similarity steadily increased toward 1, and this means the state direction becomes more and more aligned with the final representation. So the model is not just changing randomly across iterations, it's moving toward a stable final direction. Second, they measure the relative update norm, where they divide the norm of the difference of hidden state with the norm of the hidden state itself. And this value is large in early iterations and decreases over time. This means the model makes big changes at the beginning, then smaller changes later. This supports the coarse to fine interpretation Like early iterations perform large geometric corrections, later iterations perform fine-grained refinement. Third, they measure the feature norm, like this, just compute the norm of each hidden state. And interestingly, the norm does not decrease or converge to a fixed point. It grows throughout the iterations. This means that the hidden state does not converge to a fixed value in Euclidean space. Putting the three plots together, the recurrence is understood as directional refinement. The cosine similarity increases, but the direction aligns with the final state. But the feature norm grows, so the state does not converge to a fixed feature value. Therefore, the model refines the direction of the representation rather than converging enough norm, like converge to a fixed value. This behavior is also similar to that of prior work of block recurrent VIT I mentioned in the introduction. In this work, they also observed that feature directions can become more aligned while norms continue to grow. And this suggests that this trend may be a broader property of transformer depths, and transformers may use depths to rotate or align representations in feature space, rather than simply converge to a fixed magnitude. Then a natural question is, if the norm keeps growing, why does the model still work? And the paper explains this phenomena using the decoder layer norm of decoder. The decoder starts with layer norm, so it normalizes the feature magnitude before decoding. And because of this, the raw norm growth is less harmful, and the decoder mainly sees the normalized direction of the representation. So the model can allow the norm to grow while still producing stable outputs. To conclude, Déjà shows that shared recurrence is promising alternative to simply stacking more transform layers, and their main insight is that in 3D reconstruction transformers can act as iterative refinement, and repeated computation can improve geometric consistency without requiring many independent layers. But there are also some limitations, like performance is limited to the trained key range, so the model cannot extrapolate to much higher iterations. And also the recurrent block reduces parameters, but not the blocks. Like since the same block still need to be executed multiple times. And finally, they analyzed this phenomena empirically, but not theoretically. So it would be really interesting research direction to explain this phenomena in theoretically. Finally, I wanted to briefly introduce similar ideas applied to LLMs and VLMs. Since many people in our lab are interested in these topics, I searched for recent work that use recursive transformers in LLMs and VLMs. Actually, I haven't read these papers, but if you're interested, they could be good papers to check out. And it might also be interesting to compare these papers with Déjà and think about how recurrent transformers act differently across 3D vision, LLMs, and VLMs. This is end of my presentation, and thank you for listening my talk.